Hey guys, today we're going to continue our discussion in chapter 1. This is going to lead us into our talk about something called isotopes. So up until this point, we have talked about atoms, we've talked about subatomic particles, and today we're going to talk about average atomic mass. So just as a quick reminder, subatomic particles that are present: protons, neutrons, electrons. Protons are positively charged particles in the nucleus. That's what defines a particular atom. We can find that information up here at the top of a periodic table. So 2 protons in every atom of helium. Neutrons also have a mass, but neutrons are neutral and they are found also in the nucleus. And then electrons are negatively charged particles found in the electron cloud. They do not have a mass. So this average atomic mass that we see at the bottom of the periodic table. Well, before we can decide how we got this average atomic mass for helium, we need to talk first about something called isotopes. So our discussion about isotopes is going to put a few tools into our toolbox so that when we come back and build this idea of average atomic mass, we'll have the correct tools to build that understanding. So the first tool, the first thing we need to learn about is something called isotopes. So here is an experiment that the scientists were doing that helped them discover this thing called an isotope. So what we have here is something called a cathode ray tube. So what they have down here is they've got a stream of neon gas that's coming into this tube. We've got a focusing device, so it just takes our neon gas and focuses it into one kind of stream. Then we're introducing this gas to a magnetic or an electric field. So all this is going to do is it's going to cause the beam, instead of going in a straight line, it's going to cause it to bend around this curve. So that's what the purpose of that is. And then over here, we've got our detector. So scientists put in a stream of neon gas. They bent it around a curve. And what they expected to see was we put one stream of neon gas in, we get one stream of neon gas out, right? Not so much. What they saw on the detector was 3 different spots where that neon gas landed. So the first spot was here on the bottom, the second one was in the middle, the third one was on the top. So I put one stream of neon gas in, I get 3 streams of neon gas on the other side. And just to be clear, what hit the detector over here was still neon gas. So what could cause this separation of these streams of neon gas? Well, the separation was caused by mass. Okay. So we put neon gas in, we reflect it around a curve, and the smallest mass came out here first. So think motorcycle around a curve. Nice tight curve, comes around fast. The largest mass came around last here. So think semi-truck around a curve. It goes nice and slow, and it takes a nice wide turn. So we have one stream of neon gas going in, 3 streams of neon gas coming out on the other side, and these 3 streams of neon gas all have a different mass. So what's the difference between those 3? So think about the subatomic particles. Do they all have the same number of protons? Yeah, still neon gas, right? So all of them still have the same number of protons. They have 10 protons. Do they have different numbers of neutrons? Very possible. So we know that if we vary the number of neutrons, that could change the mass of that particular atom, right? Neutrons have a different mass. So it's very possible that these have a different number of neutrons. So that's what an isotope is. An isotope is an atom that contains the same number of protons, but varies in the number of neutrons. So here we see 3 isotopes of neon. So in this first isotope of neon, we see that it has a mass of roughly 19 AMU. Next isotope of neon, mass of 20. Next isotope of neon, mass of 21. So what we see is as we go down this chart, the mass goes up by essentially 1 AMU. So that tells me the difference between neon 20, neon 21, and neon 22 must be that we're adding a neutron to each of these. So that's an isotope. Well, we're chemists, and we symbolically represent everything. So we've got a symbol that will tell us this information. So here's how we symbolically represent an isotope. So symbolically representing an isotope, the first thing you'll see here is the chemical symbol. So if I were talking about one of those neon examples, the chemical symbol would just be Ne. The number here on the bottom is something we've seen before. So the number on the bottom is the atomic number or the number of protons. So if I'm talking about neon, the number that goes down here is the number 10. So to prove that to yourselves, or how do I know that? Look at your periodic table. You'll see that neon is the 10th element or has an atomic number of 10. So that's how I know it has 10 protons. The number here on the top is the mass number. So the mass number is going to be the number of protons plus the number of neutrons. So we're adding together the two particles that have a mass. So electrons is not included in here because the electrons essentially don't have a mass. So number of protons plus the number of neutrons. Clicking back just a second, this is also another way that we represent an isotope. So the way that we read this is neon 20, and this is also the mass number. Okay. So if I was talking about the isotope neon 20, I would put the number 20 up here. Okay. So that would be how we symbolically represent this isotope. This symbol tells us lots and lots of juicy information. So it tells me what we're talking about. It tells me how many protons it has. It even tells me how many neutrons it has. So stop for just a second and think about how many neutrons this isotope may have. So if the mass number, so we'll say mass number equals protons plus neutrons. I'm given the mass number at the top, so the mass number is 20. I know that we're dealing with neon, so I know that it has 10 protons. Whoops. I can use simple arithmetic to determine the number of neutrons. Okay, so 10 minus 20 is going to give me 10 neutrons. Okay, so neon 20 is going to have 10 protons and 10 neutrons. Okay. So looking at another example, here we see the isotope neon 21. So I want you guys to pause the video and take just a minute to decide how we would symbolically represent this, and then how many protons and neutrons does it have? Here's the symbolic representation, and this one would have 11 neutrons. All right, so that's isotopes. So what we have discovered is that in a sample of neon, all three of these isotopes exist. So the purpose of this discussion was to talk about the average atomic mass. So this number at the bottom. So you're thinking, aha, I got it. Average atomic mass. Well, I take the mass of these three isotopes, I add them together, I divide by 3, average atomic mass. That's how you got the number on the bottom of the periodic table. Nope. If you were to do that, if you were to type these numbers into your calculator and divide by 3, it would not equal this number on the bottom of the periodic table. Why is that? Well, these three isotopes don't exist in equal amounts. So it's not that we have 33.3 of neon 20 or 33.3 of neon 21 or 33.3 of neon 22. We've got varying amounts of each of these. So what we need to do is we need to take a weighted average. So a weighted average is the mass of the isotope and its natural abundance. So natural abundance is something that will always be given to you. And natural abundance is the amount of that particular isotope that you would find. So as I said, the natural abundance is something that will always be given to you. Here we see the natural abundance of the 3 neon isotopes. So let's say I had a jar of neon sitting next to me. I reach in, I grab an atom of neon, I pull it out. 90% of the time, that isotope, so 90% of the time, that isotope will be a neon 20 isotope. So 10 protons, 10 neutrons. I reach in, I pull out another atom. Down here at the bottom, 9% of the time, that would be neon 22. I reach in, I grab another atom, and 0.26%, or basically never, but 0.62% of the time, that would be neon 21. So all 3 of these isotopes don't exist in equal amounts. It looks like neon 20 exists 90% of the time, so it's the most stable, 22, 9%, and then 21 is 0.26%. So how do we take all of this information and get to the weighted average? How do we get to that average atomic mass we see at the bottom of the periodic table? So here's the formula, if you will, that your textbook lays out. I think this is a lot more complicated than it really is, but it's from your textbook, so I figured I would at least show it to you guys. But to determine the weighted average, to determine the weighted average atomic mass, we would take the mass of the isotope times the natural abundance, mass times natural abundance, mass times natural abundance, and then we simply add those 3 numbers together. The one thing to keep in mind, though, is we're not going to multiply, for example, this 19.99. We're not going to multiply that by 90. We're going to multiply that by the fraction or the decimal version of this. Remember, this is a percentage. We don't typically multiply with percentages. So we need to change 90% into a decimal. So the definition of a percentage, to the way that we do that, is 90% is defined as 90 over 100, which would be just 0.9. So if I was taking the weight of this isotope times its natural abundance, I would take 19.9924 times 0.904838. So you just want to make sure that you're doing it by the fraction or the decimal, not using the percentage. Common mistake. So here I have typed out all of this information. So what you'll see is I actually do the natural abundance first here, but natural abundance times the weight, natural abundance isotope, natural abundance isotope, plug them into my calculator, and these are the three numbers that they spit out. And then once we get to here, we just simply add these three numbers together. And then if you look here, this number is what you would see on the periodic table. So this is certainly a skill that, given the natural abundance, given the masses of the isotopes, this is certainly something that you're going to be asked to solve on a quiz or on an exam. So it's definitely something you want to practice. So here's an example. I want you guys to pause the video, go ahead and try to work through this, and then hit play again, and I will talk you through solving this one. Okay, so the first thing that we're going to do here is we're just going to organize our thoughts, organize the information. So a naturally occurring chlorine consists of 75.77 of chlorine 35. Here's the mass. So I'm going to go ahead and just make kind of a little table to organize my thoughts. So I've got chlorine 35. It's got a mass of 34.97 AMU. And its natural abundance is 75.77%. Then I keep reading here. And 24.23% of chlorine 37, and there's the mass of chlorine 37. So chlorine 37, it has a mass of 36.97 AMU. And it occurs 24.23% of the time. Okay. One thing to note, again, another kind of definition of percentages. If I were to add these two numbers together, they should always equal 100%. That's just kind of the definition of a percentage. If part of them is this one, part of them is this one, well, the whole must be 100%. Okay. All right. So to solve this problem, we're going to take the weight of the isotope times the natural abundance, weight times natural abundance. Then we just simply add those two numbers together. When I go to calculate this, I'm going to type into my calculator 34.97 times, and am I going to type in 75? No, I'm going to type in the decimal form of that. So I'm going to type in 34.97 times 0.7577, and I get 26.50. So I round it up. And we also do need to keep in mind sig figs. So this has 4 sig figs. This has 4 sig figs. So the answer that I report from that calculation can only have 4 sig figs. So certainly want to keep that in mind as well. All right, so we do the second calculation. So I'm going to take 36.97 times 0.2423. And my calculator again spits out 8.958. And again, 4 sig figs, 4 sig figs, 4 sig figs. Okay. Now to get the average atomic mass, we simply add those two numbers together, keeping in mind our sig fig rules. So now what rule are we considering? Now we're doing addition, subtraction. So we're counting decimal places. So this guy has 2 decimal places. This guy has 3. So when we cut our answer off, we have to cut it off at 2 decimal places. So plug it into our calculator. 26.50 plus 8.958 equals My calculator spits out 35.458. But if I were to report this number to the correct number of sig figs, it would simply be 35.45 AMU. So, cool thing about these problems is you already have the answer key. So where would I find the answer to this problem? Well, it's found on the periodic table. So if you go to your periodic table, you find chlorine, its average atomic mass is about 34.45. So you have all of the answers to these problems already. All right, so before I stop or conclude this video, I really want to bring this full circle with all of the subatomic particles. So here we have at the top, get my laser pointer. Here we have at the top, a neutral atom is defined by the number of protons. So the subatomic particle protons defines our element. If I vary the number of neutrons, that is called an isotope. So by varying the number of neutrons, what do I change? I change the mass, right? Neutrons are neutral, no charge. I change the mass, okay? What's the other subatomic particle that we haven't really talked much about yet? The other subatomic particle is the electron. So electrons, I can also vary the number of electrons in a particular atom. So neutral atom, we're going to assume that the protons, ooh, you need a pen. We're going to assume that the number of protons is equal to the number of electrons for now. Okay, so if it has 6 protons, it has 6 electrons, that will give us a neutral atom. We can and will, in coming chapters, vary the number of electrons. So I can add electrons to an atom, I can take them away. What does adding electrons and taking away electrons do? It does not affect the mass, because essentially electrons don't have a mass, but it does affect the charge. So I'm either adding extra charged particles, negatively charged particles, or I'm taking away negatively charged particles. And that's certainly going to change the charge to that particular atom. And we call this an ion. So I just want to introduce you to the concept, to the idea. I want to introduce you to the name of the ion. We're going to spend many chapters talking about electrons, so we'll certainly come back to this concept. So that's it for this video. I'm going to go ahead and stop it here. The next video will be doing some more math.